All right, good morning, everyone. It is October the 9th. Don't know where the semester's gone, but quickly. Just a couple reminders. We do have a test Monday on concrete. I posted some notes that I put on the board on Wednesday, mainly just the problems that will require calculations. Of course, remember that the first big question is the concrete mix design using the simplified method. And then all the other questions will just be like 2-point questions will just be from the notes. So please study for that and be prepared. On Monday, there will be no book or notes allowed for the test. Make sure you bring a calculator. All right, so today we're actually going to kind of start, I don't want to go too far, but we're going to start in the asphalt. So we kind of go back, we did chapter 1, 2, and 4, and now we go back and we go 3, and then we'll jump back to 5. But concrete is just such a large, we need so much time to cover that it is a section in and of itself. All right, I'm going to share the notes. We'll start with the kind of the introductory. A lot of this is in your book. I pulled most of this out of that. Hold on one second here. All right, I think that'll work for us. Okay, so first of all, I want to make a distinction between most of the time when you hear the term asphalt, we think of a pavement material. We think of something you drive on or walk on, in a parking lot or road. But for the purpose of this class, and I'll try to, make sure I do this, I'll say asphalt cement or asphalt pavement. There's several different words that you could use. You'll see bituminous cement or bituminous pavement. Sometimes some people even use the word asphaltic concrete or something like that, which I think is really confusing. But for the purpose of this class, asphalt, just by itself, asphalt is just the binder part. So it's just the hot liquid asphalt. And actually, we'll talk about, not a whole lot, but we'll talk about there are other uses for asphalt besides just pavements. But, I want to just make that distinction between the asphalt is to an asphaltic pavement, kind of like Portland cement is to concrete, or once again, flour would be to a cake. So let's make sure we're kind of clear on that. So, its use, they found it naturally, and I got a picture here in just a little bit, but you can search, there's still natural asphalt, that actually make their way even to the surface. And they used it many, many years ago for mummification and military weapons, maybe like on Braveheart or something. I like that movie, but where they got the burning fireball. I don't know. Waterproofing ships, though, that's probably was a very good use for a liquid asphalt. So when it was hot, they were able to, and pliable, they were able to apply it. And then, of course, when it cooled, it hardened somewhat and sealed. So once again, crude petroleum. And one thing we'll separate here in just a little bit is the difference between like a tar and an asphalt, because they're actually different. But when petroleum rises to the surface, the sun and the wind, they drive off the lighter, what you call distillates, and then that heavy residue that's left is the asphalt. And we'll get back to that as well. I think I've got a slide of that shows all the different things that we get from crude oil. And once again, asphalt, here's kind of the picture as it comes to the surface naturally. I don't think we may have some in the United States, not that I'm aware of. It's probably South America and places like that. But all right, so in way back in the 1800s, the first hot mix asphalt, and that's another term for like an asphaltic pavement. So Pennsylvania Avenue. So what do you know, right up there in Washington. And they constructed what would be considered, hot mix asphalt or something that's similar to what we use today. Here's a slide that shows. So there are some in California. I'm not familiar with that, but definitely in Venezuela they have some natural asphalt that occurs. Most of the time we drill for it and we get crude petroleum oil. So, we continue to need more and more because of the continual need, not only for new roads, maybe not so much, but the resurfacing of our old roads. And so the supply of asphalt has really increased um, dramatically. One barrel of crude oil, you might say, the asphalt is the heaviest part of that. And so the lighter distillates, once again, I use that word, would the lightest would be your gasoline. It's kind of like if you think about kerosene or your diesel oil, they're quite a bit heavier. They're not near as volatile, or I'll say dangerous, as far as the gases catching on fire or burning. So, but they will burn. So anyway, out of crude oil, we get a lot of different products that we don't think about so much. But the asphalt is one of the heavier ones. So here, I'm not going to read all these definitions, they're in your book, but when you say bitumen, or let's say bituminous, most of the time you hear the word bitumen, that's basically just the basic natural mixture of hydrocarbons that's in the ground. And so all those things, once again, from solids to up to gases, solids, semi-solids, liquids, and gases would be included in that. Asphalt is the black cementous material that its predominant constituents are bitumens. Okay, so when we go, see the next slide here. Now, here's the difference. Tar is basically, it doesn't come from the production of crude oil like asphalt and gasoline does, but it's basically obtained from the destructive distillation of coal. And it's not, so that one of the differences, like a practical difference, is that tar is not readily soluble in, say, gas. So if you got tar on your hand, it wouldn't come off, at least easily, with gas to clean up. But if people get asphalt on their hand, they can put a little gas and it's very soluble in gas and it'll clean it up. Tar actually contains a very low bitumen content, and asphalt would be relatively higher. All right, so here's asphalt versus tar. This is probably a good slide to mark if you have the notes. That showing the difference between those two, and both can be useful products, but asphalt is far more useful than tar, once again, so in a wide range of things that we use. For the production, as a production measure, the American Petroleum Institute, or API, they have a gravity, and so the higher the API gravity, the lower the asphalt content, and vice versa. So that would be useful, or relative to a refinery or some back in the processing of the asphalt material. I mean, we generally, engineers for the most part, and I use that word more like on the construction side, we're not really as concerned with this. If you had, like, around Princeton, there's 2 asphalt plants. They probably are not as interested in this because they're probably used to getting the products that work, and they know it'd probably be the one step behind that. It would be those that actually sell the liquid asphalt. So they actually do buy the liquid asphalt that they need for the production, but that's probably who would be concerned with the API gravity. All right. Once again, I've mentioned this a couple of times. I mentioned the word distillate or distillation. So distillation is a process where something's made pure, and we heat it and we remove the impurities. We'll talk about the same thing when we talk about the production of steel. So there's a couple of different ways that they do that. I won't go into that too much. So here's a really good slide. It's similar to the one that I showed you earlier with like a barrel of oil, but this one has more detail. So you can see over on the right side here, I don't know if you can see my cursor, but you can see over on the right side that asphalt is by far the heaviest. And and as you work your way up, you can see gasoline is on the top of all those different intermediate products, and the different temperatures that it might take to get to the final product. All right, here's probably a good test question, and I think it's related to one of the differences between an asphalt pavement and a concrete pavement. So asphalt pavements, if you want to write this down, I know you may have your hands full, but asphalt pavements are considered to be flexible pavements, and concrete pavements are considered to be rigid pavements. So, there's a big difference in those because of the way that they perform. We're going to spend, there's one whole set of slides and handouts that I have on pavement distresses, and they distress in totally different ways because asphalt is not only flexible, but why I thought of that on this slide is it's a thermoplastic material. So as it gets heated, it softens, and of course, as it gets really cold, you could say it gets very brittle. And so, if we don't design the asphalt properly with respect to air voids and the right type of asphalt and the right mix, we could have problems both ways. We could have problems with it being too soft and the pavement deforming and fatiguing that way. And if it's asphalt pavement is too rigid, then it's going to fatigue in a brittle way and break up. So either way, we could have problems. But so that's an important point with unlike concrete, really, we might see a slight volume change. This wouldn't even be noticeable, but it's not a thermoplastic material, so we don't have to worry about it near as much. Concrete pavement would be able to bridge soft subgrade a lot easier than an asphaltic pavement. So we'll talk a little more about that later as well. Remember, this is just primarily the introductory comments for chapter 3. So as with liquid asphalt, so here's some of the others. Uses for asphalt in construction. I'm not as familiar, of course, I think, as most people probably wouldn't be unless you're in like the roofing industry. They use a good bit of these, but so you have cutback asphalts that's produced by dissolving the asphalt cement in a solvent, and then the solvents evaporate after construction. So that would be a technique that might be used. Emulsified asphalts, you can see produced by separating asphalt in minute globules and dispersing them in water, and then the water evaporates. So it's very similar to a cutback, except in emulsified asphalt, you're using water. All right. So here are some common tests just on liquid asphalt. So once again, this would primarily be, actually, I think they do some of these at an asphalt plant. They might be required to prove some of these. So the first one is a penetration test. There's a real good picture there. The main thing is, this has to be a standardized test. So the liquid asphalt is heated up to 77, and then you just got basically a weight, it's 100 grams, and you allow it to penetrate the asphalt for 5 seconds, and then you measure the amount of penetration. Viscosity test. So when you think of viscosity, you think about a viscous fluid is like the inherent ability of a fluid to resist flow. So like when you think of oil or something like a liquid asphalt being relatively viscous, water is not viscous, at all. So there's a couple ways that they do this, but both of these are basically just measuring the amount of flow based on a standardized test of a liquid asphalt that's heated to a certain temperature in a certain amount of time. So it's kind of how that would go. And so here you can see the stiffness or response to load. So the viscosity, once again, would have a bearing on, once again, how flexible or rigid the pavement might be as it's put into a hot mix asphalt mixture related to temperature. So, we don't want it too soft, once again, or too hard. Flash point test is a safety test. So once again, this is a petroleum-based product. Not near as, once again, volatile or dangerous as like a gasoline would be, but it will burn. So this is just finding the temperature at which instantaneous flash or flame will occur. So it's a safety test. The thin film oven test is basically one step past the penetration test. So you do the penetration test initially, and that was like 77 degrees, and then the asphalt is cooled and it produces that thin film on the top, and you do the penetration test again and express the loss in penetration as a percentage. Ductility test, so basically they heat the asphalt, they shape them into these small samples, let them cool or harden, and then they basically just pull them apart. And so they're stretched at 5 centimeters per minute until it breaks. And then they kind of measure the elongation, and that is expressed in centimeters as a ductility measurement. And the last thing here is on the introductory part is a solubility type of test. And so they just take 2 grams of the asphalt and dissolve it in gasoline and filter it through an asbestos mat and see how much of the residue is left. So those are, probably the important thing there for your notes I want you to get is some of the, not necessarily the details of the test, but maybe just write down some of the general tests that they would do on liquid asphalt, whether it be, at the production stage or even some of the local asphalt plants that would have to use some of these products. All right. It's not my favorite part of that lecture. Once again, if you went into asphalt refinery or something like that, it's probably not very prominent around here, but you'd probably learn a lot more about those kind of things. All right, now I do want to go on and I want to talk about the next step here. So after we're going to move mainly to, of course, transportation type of things and the, and pavements. All right, so this is, can you see that? Super pavement wash method. Okay, good. All right, so let's see if we can just get through this one and we'll be good for today. So if you wanted to write something on this first slide here, a logical progression is, okay, so we've kind of learned a little bit about liquid asphalt, maybe some of the tests that would be, it would undergo before we would actually put it with the aggregates to make a hot mix asphalt or an asphaltic pavement. So the next question might be, how much asphalt do we put in a particular mix? Now this will tie in, and kind of the slides here will end up exactly where we ended up in lab on Monday. So, we've got a certain amount of, aggregate. We've got a certain amount of coarse fine and a mineral filler, and we're going to make a sample, and then we're going to see how it responds based on different asphalt contents. Okay, so that's the question here is what is the optimum asphalt content for the mix? All right. So this is probably, just in general here, what would the hot mix asphalt or the asphalt guys, what would they say would be some of the advantages of a flexible pavement made out of asphalt rather than a rigid pavement made out of concrete? So they might talk about the versatility or how fast, relatively fast they'd be able to pave. Of course, we know concrete is not only very laborious and it takes time to set up and it takes time to gain strength. Whereas asphalt, generally speaking, we place it, we compact it, and then we're ready to drive on it. So we talked about the flexibility of it. It's relatively inexpensive compared to a rigid pavement. Probably as far as the rigid pavement guys, they'd probably talk about the life expectancy and how much longer their pavements will last. They might talk about the ability, once again, to bridge over top of, poor subgrade, something like that. The asphalt people would say that we're relatively not affected by, ice control chemicals or, the salts and those kind of things, whereas a rigid pavement, especially one that would contain rebar, would be. And then, they would probably talk about the ride quality. So we don't you don't see many rigid pavements anymore that you drive on, but if you do go over a section of road with a rigid pavement, they're typically jointed about every 30 feet. So as you're riding, you go the boom, 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 boom like that. Whereas an asphaltic pavement that is placed well would be very smooth and quiet. So that might be a good selling point for them. All right. So, we went over the Marshall mix design as far as the lab component and went over that lab on Monday. This has been around a long time. It's named after Bruce Marshall, and he was a bituminous engineer back in 1943. Many state agencies still use the Marshall method. We'll compare that a little bit with a newer method called the Super Pave. At least we'll talk about some of the differences in the making of the samples and kind of what they're looking for and the equipment that's used in that. So here is a good picture. At lab, I told you that you make the sample. It looks like a hockey puck. It kind of looks like that pervious concrete sample that I showed in class. So it's 4 inches in diameter and 2.5 inches high. And so we compact that depending on the level of traffic that's anticipated. Okay. And once again, so here's the slide. So what's the purpose of the Marshall method? Well, it's to determine that optimum asphalt content. That's a good test question. So I'm going to ask you that. So make sure you mark that one. All right. So this tells you about the specimen. Again, 4 inches of diameter, 2.5 inches high. And what we're going to do is we're going to vary that amount of asphalt content. We're going to produce, like 5 different specimens based on the varying asphalt contents, and then we're going to go through the test just like we talked about. We're going to talk about the Marshall stability and flow, and then we'll do the voids analysis, and we'll be able to kind of plot our results and choose the optimum asphalt content. So different aggregates, when you are evaluating something like the optimum asphalt content, or really this has probably worked for anything in this realm or ideal of finding by changing one thing at a time in the mix. So we can't go to changing around the coarse aggregate, fine aggregate, and the aggregate mix if we're evaluating and trying to come up with an optimum asphalt content. So we just want to change one thing at a time, kind of like I usually call it like a sensitivity analysis. So we just change one thing and see how it changes the results rather than trying to change multiple factors. So we do, typically one of the things we want to do with the aggregate is we want to do a wash test, just like we did in class. And we want to determine the amount of mineral dust. Now, another way to put that is determine the amount of material passing the 200 sieve, just to make sure there's not too much there that would inhibit a good bond between the aggregate and the asphalt. And of course, specific gravity would need to be determined, or we could maybe determine that or obtain that information from the quarry. All right, so the first thing we do is we heat the asphalt and the aggregates, and we mix it all together, and then we make those Marshall specimens again. So we're talking about like a big hockey puck, and we're going to compact that just like you saw in the picture earlier, depending on the anticipated traffic, either 35, 50, or 75 blows per side, and then we just allow the specimen to be cooled. So you can see a picture here. He's actually standing over a Marshall compaction piece of equipment. So he's compacting that into the mold. All right, and then what we're going to do is we're going to bring it out, and we're going to actually determine the bulk specific gravity. We're going to get a measurement of that Marshall stability and flow, and we're going to do analysis of the specimen density and void content, just like we went over in class. The bulk specific gravity. So one way that we can do this again is by the use of weighing in air and weighing in water. And so we'd be able to do the calculation. The stability and flow test, really the only thing, I don't know if I can write on this. Yeah, can you see that? Kristen, can you see that circle I drew? Okay, good. So we compact the specimens and we make the specimens like this. okay? That's how they are compacted. But we test them like this. So it's a little bit odd that that's how that's done. And remember, P max here, the maximum load, is the Marshall stability value, and that's in pounds. And then this thing is going to actually squish out like, that's pretty bad, but squish out like, let's say, like an egg. And the amount of deformation measured in 1/100th of an inch is what we call the flow test. All right. So you can see specimens are heated in a water bath to 140 degrees. They're dried, and then the loading rate is applied at 2 inches per minute until failure. I just went over this. So failure is defined at P max, or the maximum load. That's the stability value, and the deformation is in 1/100th of an inch. So those are pretty straightforward. Now here's probably a good slide to mark. So if you have a mix that has a high stability value, so think about that. So a mix that is really strong, but yet a very low flow value. So it didn't deform much, but yet it's very strong. Those are on the brittle side. It's not flexible enough and too rigid for pavements. On the other hand, if you have a mix with that's very weak and just kind of smushes down easily, so it has a low stability value and a high flow value, then that's really too soft and plastic and would distort too easily under traffic. So again, we're after a good combination of enough flexibility and yet enough strength to endure and last a while. Here's a picture of that loading. So that's actually the Marshall stability / flow test. Gives you a picture of that. And then we go through the procedure that we did in lab on Monday, and you're going to do for me to complete the lab. So we will be able to calculate based on really the weight in air and the weight in water for each sample. We'd be able to calculate the percent air voids. We'd be able to calculate the percent of voids in the mineral aggregate. We'd be able to calculate the percent of voids filled with asphalt. So those things would be important for our analysis. So here's the VMA and the VFA I talked about. So there's a good picture here of this. So what are the voids in the mineral aggregate? Well, those are these voids in between, you might see in between each of the aggregate here. And so there's two things that can be in those voids. It's either going to be filled with air or asphalt. And primarily we want that to be filled with asphalt. And so you can see over here on the right, by volume here, we would have mainly aggregate, and then we would have small percentage of asphalt, and then a relatively small percent of air. And really the number that we want to see, we'll see this in the slides in just a little bit, 4% air is generally what we target. And what that allows, once again, is everything we've talked about. It's strong enough to resist the traffic, yet it's flexible enough to be very durable. So a typical asphalt pavement, we might want to last like 20 years, would be very good before it needs to be resurfaced. All right, so let's talk just real briefly here about the super pave test. So, they kind of come up and said several years ago that maybe a problem is that, if we're going to make a sample like this, talked about that, compact it that way, and then we're going to stand it up on its side to load it, that's probably not representative of what actually happens to a pavement in the field. Pavement in the field is loaded in the kind of the direction that it's placed and compacted. And not only that, it's more of a kneading type of motion. That's how traffic would go across it. So they came up with the notion of the super pave method, and the equipment is slightly different. Now, some of the old tests are still like the thin film oven test that we talked about earlier, but there's several new tests that would be involved in that. Now, as part of the problem, especially early on with the super pave, it's been around a few years, but early on it was most agencies that did this didn't have the testing equipment to kind of get on board with the super pave method. They use a performance grade type of characterization. And so they'll say something like a PG 6422. So if you're talking to someone in asphalt or asphalt placement, you might hear terminology like that. So that's just a high pavement temperature and a low pavement temperature. So high pavement temperature of 64 degrees. Now that's 147 degrees Fahrenheit, and a low pavement temperature of -22, something like that. So that might be the expected range of what that pavement would experience. All right, so getting back to hot mix asphalt and the voids, 4%. You can see in this slide, I probably want you to give that back to me on a test. And for all the reasons that we've already talked about, strong enough to handle loads, yet flexible enough to last and experience a little bit of maybe freeze thaw even in that. Here's the super pave. You want to write on this. This is a super pave. I should have had that on there. Super pave gyratory compactor. So again, it's not really just, we compact straight down, and there's not a lot of sense in that, but actually it's a more of a, once again, a kneading or, they say a gyratory type of motions. So this would be the whole purpose really behind super pave was this thought right here, is how can we more accurately represent what a pavement experiences, in real world. So, simulate the effect of traffic over the life cycle of the pavement. So that's the purpose of the super pave. So mark that in your notes. All right, so something that you'll hear when you talk about pavement design is you'll hear something called an easel, and that's an equivalent single axle load. And it's not on this slide, but it's actually an 18 kip or 18,000 pound load. Did that, can you see what I'm writing on that slide there? Give me a thumbs up. Okay, good. All right. So, one thing that you kind of get from this, if we're going to design most pavements, and you're talking about roadways on an easel, is that light, or you might say light passenger cars and trucks really have very little detrimental effect on the life of a pavement. We're really interested in that heavy truck traffic. So what we want to do is estimate, and we'll go through, whether we get to it today or next Wednesday, we'll go through, how you, at least the fundamental things of starting to design that pavement matrix, that thickness, and different types of the asphalt even that you would want to use based on that heavy truck or the easel, the equivalent single axle loads, because cars and trucks that, just passenger cars and trucks have very little effect on it. Here's a comparison between the Marshall and the Super Pave. So both systems target that 4%. That's been that way for a long time. So that seems to be what works. And basically just the way that we make the way that we fabricate or construct the specimens for testing and the tests that it goes through. All right, here's another good slide on if we get too many air voids. So we have two problems, and I didn't even talk about permeability. So we got too many air voids. Water can penetrate into the pavement. That's always a bad thing, especially like around here where we have freeze and thaw. And so it'll crack and break up and heave and a lot of bad things when water enters into the pavement. So too much air is not a good thing. And if we have too few air, we'll talk about this. This is a form of pavement distress. We can have rutting and premature failure and other ways. All right. So here's some, I know I had you guys make some plots for me. Here's some example plots for the Marshall method. So yours might be very similar to this. Keep in mind, it's best to have like the asphalt content on the horizontal axis, okay, and be consistent in that. So here's your air voids, or I think we call it VA. Here's what that relationship might look like. Okay, so as the asphalt content increases, your air voids are going to decrease. Remember the slide that was like this. So, you know, we've got aggregate, and then we've got asphalt, and then we got air. And, you know, here's our VMA, here's our voids in the mineral aggregate. So if the asphalt content increases, the air void has to decrease. So that should make a lot of sense there on that one. All right, and here's your voids in the mineral aggregate. Okay, you kind of see how that one would work. Then here's your voids filled with asphalt. So obviously as the asphalt content increases, and the percent of voids filled with asphalt would increase. Unit weight may surprise you a little bit. Sometimes the unit weight will actually drop off just a little bit like that. You can kind of see that tendency here if we were to keep going. So as the asphalt content increases, here's what's going on with this one. Is at first the unit weight's got to increase, because here's that same slide again, because obviously the asphalt weighs more than air. So we're just kind of increasing. And then all of a sudden, if we get to a point that we can't replace any more air, then we're going to be replacing the aggregate. So that's why it would start to drop off. And then here's some typical, what I want you to see here on the stability is that really as the asphalt content goes up to the right here, your stability is going to go down. This is probably not a good point here, but you can see why they kind of used the regression and showed that as this goes way up, your stability is going to go down. And just the opposite here with the flow. So as the asphalt content goes up and we get more and more, we're going to kind of get that relationship, a direct relationship with the flow. All right, so here's what we do. We go back to the very first slide, and we take an air voids content of 4%, and we pick up an optimum asphalt content. So in this case, maybe it's 4.7. And then we have criteria based on something like this. We might have to pick up this later. I think we're just about out of time. And we would check all the others. So we'd go back into these others and say, okay, well then what's the, what's the stability value at 4.7? Or what's the, one of this? And we'd see if it meets this criteria. All right, so I'll actually pick that back up at the very end of that. We'll go over some of that on Wednesday, but that should help you with your lab on Monday. And if you need a couple extra days, I can give you that on your lab. All right, I feel that was a whirlwind. You guys have a good weekend. And if you have any questions for the test, let me know. And I will be glad to answer the best I can over the weekend. Probably email will be the best way to get a hold of me. Thanks. Have a great day.